No, I was asking Alan because I was sitting next to him in the physics lecture, and it would be a Calc 3 lecture, basically. Somebody in here was in their class. Matt, how'd you find lecture today?
It was, I think it went by very fast.
Yeah?
And we were just jumping stuff in there.
The projectile problems. Yeah, I have all kinds of projectile problems. Let me see if I can pull one out real quick. I'm recording now, by the way. I should just.
I did a couple of, I did an integral on there, but I think I sort of broke into one of the dimensions.
Yeah. See if I have photos.
You're talking about 250?
Yeah.
There actually, there is like a lot of Calc 3 vectors and things that would help you.
Yeah, vectors, yeah, that's, we went over that, yeah. We said that there's all like vector calculus.
When you take that,
Yeah.
But then if you take Calc 3 first and then take physics, then it kind of goes the other way around.
Oh, really? Then try taking some time.
Well, I can't find it. I have a cool picture of Steph Curry problem as projectile. And projectiles you can do in 2 dimensions or 3 dimensions and stuff. So, anyways, I can't find it. So let's just move on. We're already recording, so here we'll take a quick look at 2.6 and take a look at some numerical techniques, or one particular numerical technique of first order, finding of first order differential equations. Now, I think in reality, when you're given a differential equation and you're asked to find the solution, in some cases, or in most cases in real life situations when you're actually faced with a differential equation, you don't really care much about the function. What you want to do is you want to evaluate the function at a particular point. And so you care more about where this is going instead of what the function is, so you can plot the point. So in other words, if you have a differential equation and you're looking for the solution and you're given an initial value problem, you might be just concerned about what's happening at a particular value. Oh, that should have been x1. You want to see what's going on at a particular input value, and then this is what you really want to get out of it. And in some cases, you don't care about what the function is or what it looks like. You just want to get these values out. And so with numerical method, what we're going to do is we're going to try to approximate a solution, and we're not going to necessarily find the function, but we're going to approximate the solution at a particular point. Does that idea make sense? Okay. The way we're going to do this is by finding slopes. What we're going to do is we're going to really heavily rely on the initial value, and then according to the slope fields discussion that we had in the beginning of the chapter, we can see that at each point x and y, we can plug that into the right-hand side of your equation in standard form or whatever form it's called, and then find the slope, right? So now you have a slope and a point. We're going to make a line and then take a small step and then get to another point. Now from this point, you're going to find the slope here, and then now you have a slope and a point. You're going to take another small step, make a line, take a small step, and then now you're in a new point. So you're going to keep following this same strategy, and chances are you're not going to get the exact value. but you're going to get a pretty good approximation. Okay? Do you see the picture? The steps of how to get to that?
Like underneath this.
Yeah. No. Euler's method, yeah. That's the thing. Thanks, guys. I was trying to think. Is it Newton's? No, Newton's something else. Yeah. So Euler's method, this method of taking steps, finding the slope and then taking a step, and then you go to a new point, find the slope at that point, take another step, go to a new point. That's Euler's method. And then, so what we're going to do is we're going to do some numerical calculations of this, and I think it would be good to do one that we already know the answer to. But in reality, if you already know the answer to that, you can just plug in the point, right? In reality, you'll get a more complicated differential equation that you would be using this for. And also in reality, there are functions in MATLAB and functions in Mathematica and whatever else program that you come up with where you can easily do this without having to go through the steps that we're going to go through. Also, yeah, some of those functions are built in, and there are other more, they call it robust, more robust algorithms that would get you to the point faster and more accurately than Euler's method. But as a first numerical calculation, I think this is a good step. Think about it as using rectangles to estimate the area under the curve, and then later on you get fancy with the trapezoidal rule and Simpson's rule and stuff like that to get something more precise and something quicker. So Euler's method would be just the rectangles. All right, let's do an example. Oh, let's figure this out. So they use linearization. They call it linearization, which is essentially finding slopes and finding equations of lines. So what we do is we get an equation of a line, and then we put in the information that we need. And note that we're finding the derivative as the slope, and so that's what we put in for the slope. This is the derivative, but that's a slope. And then after you get the slope, you take a little step, you add on a small step for h. So this h is like x, it's like delta x. I was going to say x minus x naught, yeah, but think about it as delta x as a step. And then so you take that little step and you put that point into the equation of the line, and then you're going to get a new point. And so now, instead of thinking about it as finding equations of lines and stuff like that, they kind of made it a little bit more compact here, where you start off with y sub 0 as your initial point. Let me start off with a table here. So you start off with x sub 0 as your starting point, and then your y is y sub 0. And then you're going to get y1 you're going to get y1 from here after that first step. And then you're going to get y2 by taking a look at the previous points. So yeah.
That formula there with like n, the one above it doesn't exactly okay, because that one, n plus 1 is 1, so n equals 0.
Oh, so maybe this is a typo in my notes. I think these are zeros. Because that, yeah, that's what the previous thing. So if you're copying this, or if you've downloaded this Maybe I should change that in my actual notes now. All right, good eye. All right, so let's do something simple like just an exponential. Oh, Ziki. Oh, yeah, maybe that should be, technically it should be xy. Boy. It kind of mathematically matters once you've established it. And so it looks like I'm using xy further in the paper, so it should have been xy from the beginning. Or I give it as yx, then that means all the things switching later on. So I guess among friends it doesn't matter, but when you're writing something, writing a paper, and you want to share it with colleagues, I think it does matter. So are we friends or colleagues? Or both? Yeah. We can be friends. All right, example. So now, is everything all fixed up here? I hope. The zeros, the ends. Okay. So for this, I usually like to use Excel. It comes up with nice numerical values and stuff like that. We can go fast, and we can just, click and spread. So my Excel takes a little while to boot up, so let me boot that up. And go on to the next page and start our problem. So let's do a simple example. dy dt is equal to, what is it, y, ky. Let's find a value for k. Let's put 0.3 y as your differential equation. And so we'll start off with an initial condition. 0 is usually a nice place to start. Let's start with 0 because it's a nice place to start. And then we'll go, we'll just go y of 0 is equal to 2. So this is f of xy right here. If we're looking at the notes, we have y prime is equal to f of xy. And again, this is an autonomous differential equation where the independent variable is not included here. We just have the dependent variable. And by the way, we know how to solve for this, right? This is... So let's pretend we do all that separable stuff. Y is equal to 2e to the 0.3 t. Is that right? Better check. How do you check? You take the derivative of this and make sure it's dy dt is equal to 0.3y, right? Yeah. And then if you check, then you say, oh, okay, that looks right. All right, now let's go somewhere. So the actual problem will ask, find y of y of 2. They usually don't want to go very far from your initial x value, because the farther you go, the more error you're going to get, of course. So we have a solution. Now we can solve for it. Again, we're doing this just to compare answers. Actually, let's solve for it later. So let me just leave that blank for now. But let's go through the process of Euler's method to see if we can get to this point at a reasonable number of steps. So we need an h. h is going to be the step size we're taking. We're going from 0 to 2. This is 0. X is equal to 0 to, we want, this is your final x value. And so let's pick an h that would be nice and simple, the step size.
0.5, 0.25.
Let's do 0.5 first. H of 1 would be a pretty big step. Let's do 1 first and make this kind of as raw as possible. And the larger your step is, the less precise you're going to be. The smaller your step is, the more precise you're going to get. And so we have y of 0 is equal to 2. We have y of 1 is equal to, now this is where we want to start using the formula. It is equal to y of 0 plus the step size times the derivative, or times the function itself, which is the slope. So this is 0.3 evaluated at 0, 1. And since there's no x's, we don't put the 0 in anywhere. This is h. H is 1. Yeah? So in your f of x naught, y naught, we're going to put y naught wherever we see a y, and we're going to put x naught was 0. We're going to put x naught wherever there's an x, right? But our derivative didn't have an x, so we're really just putting y naught. Does this make sense? Are we? I got some nodding, but there's some.
Well, show me the next one.
Okay.
Y2.
So I should put my x-axis here too. So our y. Our x sub 0 is equal to 0. And x sub 1 is going to be 0, the initial value, plus the h step that we took. And then in the next step we'll be done, because it takes 2 steps to get there. So this is going to be 2. Just add 1. And so y of 2, which is our solution in this case, is going to be the previous y value. Oh, we need to compute this. 2 plus 6. 2.6? 2.6. So now we're going to go 2.6 plus our step size times f evaluated at the previous point, which is 2.6, or which is 2, 2.6. Again, this is the previous y value plus h, which is going to be the same, times f of x1, y1, and x1 was 2, but that doesn't matter because there's no x's in our equation, our differential equation, and y1 was equal to 2.6. And that's what y1 is equal to. Okay? So now we can work this out and say this is 2.6 plus what is this? 3, 13, 39, the whole thing? 3.38. So this is 2.6 plus what? Sorry. Okay. So I guess we have an opportunity to see how this thing looks like graphically.
Professor,
Yes.
I wonder where the 1, 2 plus 1 is.
Oh, the 1 is the step size. So we're taking step size of 1. Later on, we'll take a smaller step size of 1/2, and then we'll do one with 1/4. All right, so let me put the points in first. We have 0, 2. My tab's not working. We have 1 and 2.6. And then we have 2 and 3.38. So these are the points that are leading towards that. We should draw the lines that connect them, but we'll come back to this. We'll come back to this graph a little bit later. So I just want to establish those points for now. All right, let's try a different step size. Where it'll be a little smaller, and the smaller step size, the more precise your graphs will look like. So we'll start off with the same x naught and y naught. So, but this time our step size is 0.5, so it's going to take me more steps to get there. So this is a give and take. You're going to get a more, with a smaller step size, you're going to get a more precise value, but it'll take a lot more work because you have more step size, you have more calculations. So we're going to go all the way up to y sub 4. The first one we just did y sub 2 because it just takes 2 steps to get there and we're done. So now we want to go to y sub 4. And we're going to go through the same process. So y sub 1 is going to be y naught plus h times the derivative evaluated at 0, 2. So again, there's no x's, so there's no 0 to put in. We'll put 2 in for, I guess I didn't need that extra parentheses. Yeah, it just makes it a little bit easier. So we need a value for this. What is it? 2.3. Y2 is going to be, now we're going to use 2.3 for our new y value and 1 for our new x value. So we're going to say 2.3 plus h times f of xy. So this is 0.3 times the previous y value, which is 2.3. And this one is 2.64, 645. So I'm looking at y sub 2, and I'm comparing that not with y sub 2 from the previous problem, but when x is equal to 1. So I make a comparison. If you're going to make a comparison, you're going to make it with the same x value. So with the x value of 1, I got 2.6 here, and I got 2.645 over here. Right? Let's go one more. I guess we'll finish this off. 2.645 plus the h 0.5 times the f function, 3 times 2.645. Gets a little tedious. But if you didn't have a computer back then, right, you'd do all these calculations by hand to get a more precise value. 3.05. So the next one is going to be y, the previous y, which is 3.05 plus 0.5, 0.3 times 3.05. And in our last calculation, we should get something close to 3.38, right? I hope. What is it? 2.51? 3.51. I don't know if that's close, but yeah.
That's the Lewis method applicable for all time.
First order. Only first order. So we have autonomous. You can make this as complicated as you want, and then something that we definitely can't solve for, and then you can certainly use this to make your approximations.
But I mean, what if we are asked to find a 100 terms?
Well, it's still possible. You just have to, figure out how much error you should expect. And if you have Excel, you can. It'll be a long spreadsheet. If you have a computer, if you know how to program in Python or in C++ or whatever, you can certainly generate something like this. You come up with a new function, have it recursively. That's the other thing, is that these are recursive calls. So, it depends on how much memory you have in your computer to be able to run this before it crashes. Yeah.
Clarify what the x and y values in your correspond to, because the y's I see, but the x's.
The x's you don't see because we're not plugging it in here. But the x's would be the steps. So a step of 0.5 will give you an x of 0, 0.5, 1, 1.5, and 2. So those are the x values.
So why are we not putting those into our f of
Because
y bar?
maybe I should have come up with an example where this has an x, but in our problem, in this particular problem, we have a differential equation that doesn't have an x on the right-hand side. Normally we would take these values and put it in, but we don't have that. Yeah, one more?
I mean, it looks like a geometric regression.
It is, because this is an exponential function, so there's a geometric relationship here. Again, if this is a different problem, which we should have done something different. Because the reason why I wanted to do this is because we know the solution off the top of our head, or some of us. Yeah. I mean, you separable, you do it, and if you do it 50 times, then you'll have it memorized.
So, does that mean that we can use the geometric regression to find formula and get the 100?
Only for problems that look like this.
But
If
it's not.
if I put a plus x here, then that's not geometric anymore. Totally different.
But when it's x, like when it's t, right?
Oh, or in this case, t, yeah, the independent variable. Oh, I should change this to x, because I'm using x's for everything else. Let's find out the real value. Can somebody put two in for x here? So this should be the exact value. And the first time we got 3.38, the next time we got 3.51, so it looks like we might be getting a little closer. Yeah? Did you have another question? Observations?
Yeah, it occurs to me that we can always make it be a geometrical function.
For this problem? Yeah.
I mean, always, whatever x and y is equal to.
No.
I think
Okay, we'll take a look at a different problem. Let's try 0 and 2, 0.5 and 2.3, 1 and 2.645, 1.5 and 3.05. I should have just done this all in Excel. And then 2 and 3.51. And since we actually know the solution, we can also graph the solution. Y equals 2 times e raised to the 0.3 times x. Maybe I should make the first ones blue. So, this is the picture right now. If you follow the blue dots, we're going a little bit lower compared to the red dots, and the exact solution is in green. So, because we're taking more steps with the red dots, we're going to get a little bit closer. We're going to refine it to be a little bit closer. So that's what's helping us get our values quicker. Okay. Now let's actually try to do this in Excel. And let's start off with our x values. And if we take h to be, let's do h.5 again, since we've already done it, and just to kind of confer what it is we're looking for. When the subscript is equal to 0, 1, 2, 3, 4. When x is equal to 0, when the original point is 0, 2, right? Or is it 0, 2? So in each step, we're gonna take a step of 0.5. So I think I can just scroll that down. And then for our next step over here, what we're going to do is we're going to take our previous y value, and then we're going to add the step size, and then we're going to multiply it by the function 0.3 times y, right? The previous y value. All right, that's wrong.
Even multiplications on 2.5.
Oh, jeez.
Yeah.
All right, so it's 2.3. That's what we got. And then we can just scroll down here to get our values. So it looks like since we rounded off over here 3.05, this is going to give us a more precise value. So this is a step size of 0.5. Okay? Let's do a step size of 0.25. So we'll start off with the same initial values over here. And then instead of 0.5, we're going to take steps of 0.25. So it's going to take me a little bit longer to get to 2, because I'm going to have more intermediate steps. And what was the formula again? The formula was just to pick the previous formula. So it starts off with the y value from before plus the step size. The step size is actually 0.25 times the slope, which is the dy dx is equal to whatever that right-hand side is. And it only involves the y value. So now if I figure out what happens here, I got 3.56, which is again closer to our value. Our exact value was 3.664. Okay? So this is with step size of 0.5. Now we can take more steps and take step size of 0.1. Should we do that? Sure we can, because this is Excel. I just copy and paste a whole bunch of things. It's take me a little bit longer to get down to 2. Oops. Here's 2. And now my step size is 0.1. And then I click and drag. And 3.61. Okay? So you could do this, again, using a computer program, something that you might be familiar with. See if you can run some recursive functions that call on itself to get those values. So this example is an example where we have only a y value, which is, I think, throwing some people off. So let's do another example. Should we include some pictures here? I think this picture is a good picture. All right, let's do another example.
Show that picture one more time? Too late.
No, it's not too late.
Thank you.
I wonder if I have an example in my notes. Do I have an example in my notes? Six, 7, or 8?
8.
Wonder if I can draw slope fields here. Nah, I don't know how to draw slope fields here. Oh well. anyways, if we think back on some of the things that we've been talking about, is this separable? It's not separable. Is it a linear? It's not linear because the y is taken to the square root. What else? Is it exact? I don't think it'll be exact when you solve for it. One of them is either going to be 0 or 1/2 square root of y to the negative 1/2, so it's not going to be exact. It's also not autonomous because there's an x on the right-hand side, right? So yeah, so I don't know if we can find a value for this or a solution for this. So let's just go ahead and see if we can just find approximations. Let's do some by hand, and then I'm going to probably click over to Excel in a little bit. But let's try to get the idea going on here. So the right-hand side of your differential equation is your function that you're going to be dealing with, f of x or f of xy. And then we have our initial values at 0, 1. So our x of 0 is equal to 0, or y of 0 is equal to 1. And we can use this to help develop our values. We want to get to 0.5, and so they suggested a couple of steps. They suggested steps of 0.1 and steps of 0.05. So let's take our steps to be 0.1. And so we can list our y value, our x values already. So 0.1, 0.2, 0.3, 0.4, 0.5, and this is where we want to end. So in our first step with the h values, with the h value of 0.1, we're going to get, we're going to look for 5 y values. Okay? So how do you find this? Well, I want the previous y value, which is 1, plus our step size times our function. So this function now has an x and a y. So I want to put the x value that I had and then the y value plus the square root of the y value, and then that's my function. And that's f of x naught, y naught. So our x naught and our y naught. So I believe this is just going to be 1.1. Right?
Looks like that.
All right, so now my y1 and my x1 are given, so I have to look at my x1 here. x1 is 0.1 from our step, and then we go to y2. Our y2 is going to be the previous y, which is y1, so that's 1.1 plus the step size of 0.1, that's your h, times the previous x naught, which is 0.1, times the y value, which is 1.1, plus a square root of the y value, which is square root of 1.1. So $1.216. Okay. And then we can go on with y3, y4, and by the time we get to y5, we would get our x is equal to 0.5 at that point. So this is going to be our solution. Okay, so let me move over to Excel now. And I'll have my step 0.1 here. And then I'll write my x values, my y values. So my x starts with 0, and then 0.1, and then we'll take those steps until we get to 0.5. My y sub 0 starts at 1. And then now comes the formula. So it's going to take the previous y value, y sub 0, plus h times, in parentheses, is going to be my function, x. So this is my previous x value times my previous y value plus the square root of my y value. And this is the 1.1 that we got when we did it. The next one is 1.216. And then keep going to get our estimate. So it's going to be about 1.69. 1.690. So that's another thing you have to be careful about. If it's asking for 4 decimal places, you want to try not to reduce, not to round off in your previous steps. I guess that's to say that don't do it by hand. So when x is equal to 0.5, our approximation is 1.6902. Okay? All right, let's take a smaller step of 0.05. And do the comparison. So this will take 10 steps now, instead of 5 steps than the one that we saw before. Just copy and paste this and change my step size to 0.05. But everything else will remain the same. It'll just catch the 2 previous values. And then that'll bring me to 1.7219 for 4 decimal places when the step size is 0.05. So we went from 1.6902 to 1.7219. For a better approximation. Of course, you could take more steps. You could take steps of 0.001, and then if you take steps of 0.001, you'll need to do like 50 of them. But if you're letting your calculator or letting your computer figure it out, then that's not a big deal. Okay. So just remember, you can actually graph this, right?
So it's not like it was.
Well, I don't know if I could show you how it goes. I could show you the graph.
Whenever I try to graph something, I always end up with the x's values being their own line and the y values being their own line.
Oh.
Like, how do
I got a.
how do you do that?
I went to insert and charts. Now, in charts, there's a bunch of different possibilities that you can pick, but there's one called a scatter, and then you can kind of see a scatter plot. And that will take a look at the two columns that you highlighted and say, okay, this is the x, this is the y. I think it's x's and y's. Maybe it's switched. No, it's right. So it's 0 to 0.5. My x values, and then I'm getting this point. So if you want to do a comparison, remember that these points over here, I can't just copy and paste, right?
Your quick and dirty way is to take the table on your left, hold all the numerical values, copy it, press copy, then the cell on 9, row 9, at the very left, A9, click paste, highlight all that chunk, do a data sort, so you get duplicate values. I don't know if this is fast.
I might have one too many here.
No, you want that one.
I do?
Yeah.
Okay. So data sort by what?
Just maybe just base the other way. Although it's all formally with base. Does that mess up all the values?
Yeah.
All right.
Unless you can copy it as copy it as the values and then sort it that way.
Yeah.
So I basically want to, let's see. What I basically want to do is I want to include these values, but I can only include these values according to their x values. So this is a 1. I don't have a value for that. This is a 1.1. I don't have a value for that. This is a 1.21588. This is a 1.35047. This is a 1.50719 and 1.69024. So now should be able to come up with a double plot here. Nope. Yeah. They're in there. So I need to zoom. These approximations are pretty close to each other. Relatively speaking, if you blow this up so that you're zooming in enough, you can see the difference kind of get bigger. And so you can see it slightly, and I'm not too well versed with Excel that I can just zoom in or zoom out. There's a way to zoom in and zoom out, adjust your Y values and X values. So I'm not going to do that. Okay. So that's the idea behind this particular numerical method. Later on, I don't know if we'll have time, but later on there's another method called Runge-Kutta that's going to be a little bit more robust, and you can get to your solution faster and more precisely instead of this, but it requires more, more numerical stuff. So if we have time at the end, towards the end of the semester, we'll take a look at that. But like I said, most problems that help you solve differential equations actually have the Euler method and Runge-Kutta method, and there's another version of Runge-Kutta 4 that's all built in to their programs, that you don't really need the algorithm to do that. You just type in your differential equation. So we'll not worry about that. Okay. Questions? I didn't mean to talk this long about this subject. I usually skip it, but we're here. It's done. Let's move on. Which means your whole lecture on Chapter 3 will just be 10 minutes. So Chapter 3 basically now goes into modeling, which is to say word problems, which is physics. What was that?
Didn't we already do the homework about it?
I don't think so.
We already did one.
The Newton's law of cooling, including the argument.
Section 1.3.
Oh, so that section has some of that simple stuff. Okay. For some reason in this chapter they wanted to go deeper into more application problems. So in section 1.3 you did Newton's law of cooling. Did you do anything else? Do you remember? Kirchhoff's law, so you did some circuits. Anything else?
Population of affected students.
Okay, so population growth, that's like a logistic model. Inflow and outflow, so that's mixing. Wow, you guys already did all that stuff. So why did they do this?
Where are those notes? By the way?
I just not up yet. No, because these things are solvable somehow, some way. You can solve them. In fact, if you go read through the chapter, you know, they'll show you the application and then they'll tell you how to solve it. Oh, yeah, that one. Yeah. That's in 1.3, right?
Yeah.
Let's see.
Gravity.
Oh, I think in 1.3, all you had to do was set up the differential equation. You didn't solve for it.
Correct.
Okay. So this chapter tells you how to solve for those differential equations. Really? Yeah, once you have the equation, you just do the stuff that we were doing in Chapter 2. So I'm going to see if we can go into our WebAssign and maybe we can try to do one problem from Chapter 3 just to see how it might look like. And I should have had this up already. Yeah, we did substitution. 2.5 is substitution. What?
My answer was completely off just by a mistake getting one constant.
Watch out, sometimes it says estimate.
And then you have to put in a numerical value. All right.
3.1.
What are we looking at? Let's take a look. Let's take a peek at 3.1. Oh, these are going to have answers. I want ones. Made
unique entries.
made that mistake before.
All of these ones have, except for number 6. Number 6 doesn't have unique entries.
What is that homework that says temp? That one?
Oh, I don't know. Let's just ignore that.
Oh, that's that one.
Yes, I have 10,000 notes. Or 10,000.
Oh, you want to do a dead body one? So this one, just like 1.3, or unlike 1.3, 1.3 was looking for equations. Here they want you to actually solve for it. So if you know the equation already, that's going to be a big plus. Otherwise, you kind of have to, find the equation first and then solve for it. But if you look at the book, most of these have already been solved for. These are like the standard classical differential equations where people would already know the solutions without having to go through the process of solving for it. Like this one, except I don't remember. Yeah. So a dead body was found in a closed room in the house. The temperature was constant at 65 degrees. And at the time of discovery, the core body temperature, I guess they're assuming it to be 85 degrees Fahrenheit. 1 hour later, a second measurement showed that the core temperature was 80. So I wonder why they didn't go 98.6, which is like the usual body temperature. But so the body temperature when it died was 85 degrees. And then an hour later, an hour later, a second measurement showed that the core temperature was 80 degrees. Assume that a time of death corresponds to time 0, and the core temperature, so the core temperature is 98.6. So this is some time later. Yeah. Determine how many hours elapsed before the body was found. So T1, let T1 bigger than 0 denote the time that the body was discovered. All right. So there had to be some adjustment. So Newton's law says that what? That the rate of change of body temperature is proportional to the difference between the current body temperature and the surrounding, right? Except, is this right?
Yeah, that's right. Yeah.
And do we know? Yeah, this is an exponential function. Do you guys remember what the solution was, so we don't have to go through it? It's in my notes. AE to the KT plus 65. I don't even have it here.
I don't remember it, but
yeah, that sounds familiar. So your T versus little t, your temperature T with respect to time T is going to be A e to the KT plus 65.
I can't get any colder than 65 as T blows up, the E turns that function to 0.
Yeah. Yeah, so this is like the leveling off. So your graph would look something like this, with an asymptote at 65, because that's the temperature at the house. So you can't expect the body to go below that temperature.
A is going to be the difference between 98.6 and 65.
So yeah, so think about A as what the constant C that we would normally solve for with the initial condition. And the initial condition is that when T is equal to 0, your temperature is equal to 98.6. So e to the 0 is 1, 98.6 minus 65 is whatever it is. So then your function is going to be 33.6 e to the kt plus 65. Okay? So now we have two other pieces of information, 85 degrees when it was discovered, and so they want us to let t sub 1 be the point when it was discovered. So we're going to have t sub 1 comma 85, and then 1 hour later, t sub 1 plus 1 hour later, we have 80. So what we're going to try to do is use these two pieces of information to find out what happens. Actually, we can also use 0, comma 98.6. This usually would help us find t or k. K is the other unknown that we have. And so if we use,
We won't be able to find k with the 0 time,
we won't be able to find k with a 0 time. So let's put this in to our equation. So we got 85 is equal to 33.6 e to the k times t sub 1 plus 65. And then we can put in the other value, which is 80, is equal to 33.6 e to the k t sub 1 plus 1 plus 65. So here we have a system. They're not linear, but we have a system of equations. We have two equations and two unknowns. So we can solve for the two equations and two unknowns and then get our k value, which we kind of don't need in this problem because we really want to find that t1 value, which is the amount of time it took for this person to go from its death to the time it was discovered. So, can you guys handle this? I would probably solve for k for each one and set them equal to each other, and then solve for t1. Solve for k and t1. Solve for k first for each of them. Then you'll have two k's equal to this and k is equal to that. And then set those two equal to each other, and then solve for t1. And then you should be good to go. Okay? All right, so we're out of time. Your homework is everything up to 2.5, I think. So 2.6 is something that we did today. That's not part of your homework. And then you guys can handle Chapter 3 on your own, I think. So this will be all the examples that I have for Chapter 3. Quiz, Tuesday. I don't know. I'll announce.
Was on separable and exact.
Separable and exact.
So, was that